Hi everybody. Well, as you can see, I have this thing mostly put back together. It's been recapped. We'll go more over what I did here later on. So I have one quick addendum to do to the last video that I did about the capacitors. And that is, one other thing that affects the value of the caps and the performance of them is the actual maximum working voltage. So if you look down here, and let me bring the other camera in. So if you look down here, you have three identical capacitors. They're from the same series, they're made by the same manufacturer, and they're the same value. And the only difference is this one is a 25 volt capacitor, this one is a 50, and this one is a 100 volt capacitor. Other than the voltage rating, they're identical. You know, you've heard a lot of times where a lot of folks will say online, you can always replace a capacitor with a higher voltage value just so it's not a lower max voltage value, and it'll work exactly the same. Well, to some degree that's true, but when you're talking about audio, where you're talking about using it as a coupling capacitor where it's going to conduct, where there's actually going to be a range of frequencies passing through it, in other words, it's not just a filter cap for a power supply, that's not so much the truth. And I'll show you why here in a second. So let's just look at this for a minute. We'll get the DEI LCR meter out. And if you look at the 10 microfarads at 25 volts, and again, we're testing this at 100 kilohertz test frequency, you can see we have 3.26 ohms for your ESR. And look, it's only acting as a 3.5 microfarad capacitor. Okay, moving up to the 50 volt cap, you can see already the capacitance changes, you know, the perceived capacitance at that 100 kilohertz, and the ESR drops a good bit. And of course, with the 100 volt version of the capacitor, the ESR drops even further, and look, now it's even acting like a little bit of an overachiever. So the point that I'm making is that just having a different voltage rating of the same brand of capacitor will make a difference. And just to show you, you know, when you compare it to a comparable film capacitor, this is a 50 or 63 volt film cap, you can see it's very similar to the 100 volt electrolytic, but even lower ESR, basically unmeasurable ESR. So that just gives you an idea that, again, you might think it would be better to put this bigger capacitor in here, right? But understand the way the circuits are designed by the manufacturer, they take that into account. So the voltage rating and so forth of the capacitor that they use in the circuit is designed to be in the part of the circuit that they put it in. And when you change that, you will affect how this reacts in the circuit. So I hope that kind of, you know, is helpful there. But just like we saw on the previous video, just changing some of these parameters makes a big difference. You know, we looked at film versus electrolytic, and now we're looking at low voltage versus high voltage electrolytics of the same brand, of the same value, everything. Okay, getting back to this, you can see we have this everything ready to go. I did run into a few interesting issues rebuilding this. As I said, I used electrolytic capacitors, the same type as what I replaced, you know, as what I was removing. So yes, it's a different brand and so forth, but you know, whether it was a bipolar or polarized electrolytic, that's what I replaced it with. And I stuck with basically the same voltage. I will not move usually more than one voltage step higher. So for instance, if you have a 10 volt cap and you replace it with a 16, or if you have a 25 volt capacitor, you replace it with a 35 volt, there's not enough appreciable difference to really to affect it that much. But if you go from, you know, an electrolytic to a film capacitor, or you go from a, you know, 10 volt electrolytic to a 50 or 63 volt, expect it to make a difference. you may or may not hear it. It just depends on the circuit and where it's located in the circuit. Okay, unfortunately I have a little bit of shutter roll going on here. And that's just the nature of how this all works. But I'm just going to show you very quickly on this one a couple of things so you can look at the big picture, and then we're going to go over to the image on the computer screen. But if you look on here, where's my pointers all at? See all these capacitors that are yellow that I highlighted? These are all the 2SA-726 and 2SC-1313s, which these are kind of known culprits. They fail prematurely, and they'll either get shot noise or they'll get severe gain fade where the gain will go down. And when you have gain loss on a transistor, it's going to run hotter, is usually what happens. So these ones I would preemptively replace. The cool thing is, on this one and on the other one that I have, this must be a newer production run, you know, one of the later production runs, as is the other CA-2000 that I have. Both of them have different transistors in this. They do not have the 2SA-726s. I'd have to look it up in here what these are, but they're not the 2SA-726s. So, and they're actually a good transistor. So I didn't have to replace them. I lucked out on that. So let's go over a couple of these things on the schematics. Okay, let's see how this works on here online. So if you look, we're right now looking at the phono stage, and the input capacitor, as you can see, is a 2.2 microfarad. And if I switch you over to the overhead view, you see these two caps right here, these brown ones, those are the film capacitors. So you can see they're pretty big, but for that particular position, they used film capacitors. And that's right here. It goes into your input of your differential pair. You have, this is the infamous current mirror that they were mentioning, and you know, I read to you, it showed you in the manual there on part 1, that makes sure that these two transistors are always maintaining the same current, so that this is a voltage only stage. And then you have your RIAA filter. So this is the equalization filter for the phono. And this is what removes the pre-emphasis. So this is a de-emphasis filter. And it works by taking, so you take this signal, it goes through this input buffer, goes through this transistor. This is called a single-ended push-pull, or SEP circuit. And then it drives these two, I guess we'll call them outputs, and works just like your, you know, that drives the speakers. But if you notice, the emitter resistors are 100 ohm. This is lower current, much lower output. But once again, it's a push-pull circuit. It takes the output from this, feeds it back through that filter, and then the filtered audio goes into the other input, to the feedback input, and that will oppose the signal coming in. So what it's going to do is, when you add those together, or subtract them I should say, you will get an output that is the filtered output. And the cool thing about this type of circuit design, and this is a common thing, okay, the cool thing about this is that if the amplitude or the input amplitude changes dramatically, this feedback loop will actually make the whole thing work the same regardless of what amplitude it's operating at. It's pretty cool. Thing you want to take note of, any of these things in yellow, I kind of modified the schematic. The yellow circled capacitors are film caps. The red ones are electrolytic, and specifically bipolar electrolytic or non-polarized electrolytics. And if you look, the output of the phono stage goes through this 560 ohm resistor. Why do you think that's all in there like that? And it goes through this electrolytic capacitor, but if you look down here below, there's also a 33 nanofarad film capacitor in parallel with it. And so you have to understand, they knew very well when they designed this circuit what they were doing. This capacitor, as I said, because it's electrolytic, has a different roll-off than a film capacitor. But it does shape the sound in a certain way, but you still need to compensate a little bit for that, and this is what they did. So if you put another film cap, let's say, because today you can get a 10 microfarad film cap for a relatively low price that would probably fit in here, you would change the sound signature by doing that, because the film cap that you would put in here would have a different roll-off, and we showed that using that DATS program, that DATS 3.0 or whatever, in the last capacitor video that I did. And this is why I say, in my opinion, and this is just my opinion, these were designed this way, and this is why when I replace this cap, I have replaced it with the same type, a 10 microfarad, 25 volt, non-polarized electrolytic. And I left this alone because these really don't go bad. Now moving along to your volume control board. Comes out of here, it goes through your switching network. So if you select Phono or you select auxiliary or tuner or whatever, it goes through the switches, and then it comes up through this line here, and it goes into your first volume element. Remember, this thing has 2 volume controls that are connected, that are actually ganged together. And when you rotate the volume control, it rotates this one and another one down the lane a little bit. We'll see that in a minute. So you have your input volume, and then you have another differential pair. And this does the same thing. You have your input transistor. It goes through this right here, and it goes out to your to the other stages. Now, depending on how everything is switched in here, it's either going to loop this through your tone control or your filters or both, or it's going to send it directly to the power amplifier. It's just depending on how this switch up here is. And again, you have a coupling capacitor, but this is not just an output capacitor, it's kind of an input one also. You can see you have your audio here, it's going through here. This is again a 3.3 microfarad this time. Now remember, this one was 10 microfarads, this is 3.3. Again, it has to do with the impedance and the amplitude of the signal you're feeding into into this. So you look, you have a 470 ohm, and then you have 100K going to your return line right here. So you have a relatively high impedance, so you don't need as high of a capacitance. But what this does is if you don't have the correct value here, the sound can be kind of muddy, because it'll allow a different roll-off, again, of the low frequencies as well as the high frequencies. And again, you have a film cap in parallel with it. You see that? This isn't something they do on every single preamp and amplifier out there. This is a very well thought out, well designed circuit. And again, they're picking off some of that signal from here, and they're feeding it back into here. If I move over a little bit, you can see this is the mid-range board right here. The mid-range has its own little circuit board, and there's the mid-range level, and it can, depending on if you're turning the pot, past 12 o'clock or before 12 o'clock, will be either boost or cut, and that's the way this filter network is designed. Again, it feeds into this, and you have a feedback circuit that it loops through, and again, this ensures that regardless of what amplitude of, what volume the signal is, it will still apply the same amount of attenuation to the signal, percentage-wise. You're going to find this whole circuit is like this, and most of the audio gear from this era is designed this way. The other thing is, if you go to the next step over here, this is your bass and treble board, and this is kind of a Band XL tone control stack. So you have your treble and bass. You know, it's high and low. And again, we call this an active band XL tone control because it's not just a filter. See, so let's go back a little bit. In lower end amplifiers, you would just take the preamp signal, feed it through this network. It would come out of this network and go into your power amp section. And this would just, you know, either boost or cut your treble and your bass. But the problem with that is, as you increase the amplitude of the signal going in, it will change how these capacitors react, because you have a bigger amplitude signal, which is going to change the current, which is, as you saw from our capacitor testing, is going to affect this. So by keeping everything compensated by having this differential pair, this almost works like an op amp, right, with an inverting and non-inverting input, it's going to ensure that your tone control stays stays consistent no matter what the amplitude of the signal you're feeding into it, to a degree, of course. And again, in this one, you have another non-polarized electrolytic. It's 3.3 microfarad, just like on this one. And these ones do not have a film bypass capacitor. Do you notice that? They don't have one. Why? Well, that's the way the circuit's designed. They don't need it. It's the way these things work. But again, if you put a film cap in there, it's going to change that. It's going to change how this all works based on frequency and amplitude. So I'm not saying that the film cap isn't physically a better capacitor than these electrolytics or more reliable, but I'm saying the circuit was built around the fact that it uses these components. So changing them without changing other things would affect the sound. This is where I'm coming from with all this. Now, the other thing I noticed was when I got to the F2660 board, which is that volume control board, and this is the other volume element. So they adjust the volume before the line stage and after the line stage and tone control stage. So when you turn this volume pot up here at the top, you know, right up here, you're also at the same time turning this volume pot right here. And what that's doing is that's reducing noise. So if the transistors have a little bit of noise in them or anything, you're reducing that substantially by controlling the volume at 2 points in the preamp. And again, we have another thing. Now, this is an older schematic. So if you look here, this is a 2SA726, which, you know, any of you who've watched my videos know that from the Pioneer gear, these are problematic. These get shot noise, and a pretty high number of them fail. Same thing with 2SC1313s. They'll get gain fade and things like that. So these are two transistors, you know, they're older ones, and if I see these, I absolutely replace them. The cool thing is, on both of the preamps that I have, they were later production models, production runs. They do not use these. They have an updated set of transistors, and I forget the numbers of them. I'd have to look it up. But they do not exhibit that problem. They're much more reliable. You never have to replace them. So I didn't have to touch any of the transistors in this preamp, in either of the ones I have here. The other thing was, when they changed those transistors out to different ones, this capacitor here was changed from a 2.2 microfarad. So that they had a 2.2 in parallel with a 47 nanofarad film. And this was actually a polarized electrolytic. So you look down here, you can see that it's polarized. And these are those orange low leakage capacitors. You know, the ELNAs, I think they are. And mine does not have that. Mine has the orange, they're 0.47s. And I don't believe I have that parallel capacitor in there either. Looking at it, I don't know if I could see it from up here or not. Okay, so yes, it does actually have this 0.047 in parallel with it still. So now what we have is, instead of a 2.2 polarized in parallel with a 0.0 or 47 nanofarad, I have a 470 nanofarad polarized electrolytic in parallel with the 47 nanofarad non-polarized, or a film capacitor. And it's just a change that they made, and it might have to do with the difference in the transistors that they put in there. And now that I'm in there, I should be able to see here. We have a 2SA-750, which those are decent transistors. And the other one is a 2SC, looks like 196 or something like that. No, 2SC 1951. So those are the transistors in here. They changed them. So this would be a 2SC 1951, and this would be a 2SA-750 right here. Good transistors, and again, maybe because of that they changed this. What else? Oh, a couple other things here. These are polarized electrolytics. This would be the headphone amplifier. And if you notice, these are all polarized. All of these. And I forgot to circle this one. So the things that are circled in green are polarized electrolytics. And again, these ones, none of these are bypassed with film caps, as you can see there. So now if you go back to the, and let's see if I can expand this a little more. This is the power supply, and if you remember in part 1 with the other preamp that I did, these two resistors, these 120 ohm 1 watt resistors, this one here and this one here, were both open. And they were those light blue colored resistors. Let's see if I can show them to you. I got a whole handful of them here I can show you. So right there. And they were all open. Well, strangely enough, when I checked the ones on this preamp, one of them was a little bit high. It was barely within spec, but it was in spec. The other one was right on. It was 120 on the money. But I found several other places in here. So for instance, let me switch you back over. You see right here, these blue ones? Those were those gray ones also, and all 4 of them were grossly out of tolerance, like really, really, really high. And they were that same brand. They were those same light blue colored resistors, and it seems like every one of those that were in the circuit were like that. They had drifted up. So I don't know why these things drift, and I don't know why they went open, but they did in both amplifiers. Now, I've changed all the bad ones in this amplifier. I only replaced these two in the other amp, because if you remember that other preamp, all we did was troubleshoot it and replace those 2 resistors. And I said I was going to keep that one all original and not touch it. I was going to rebuild this one totally with the capacitors, any transistors that needed to be replaced, and any of the out of tolerance resistors, which is what I did. And then in another video, we're going to compare them and try to use some novel methods of comparing the outputs of these two things, you know, a recapped one versus a non-recapped one, to see if we can see any difference. So I guess my point of all this is, check these resistors in the phono stage if you're working on one of these CA-2000s. Check the resistors in the power supply board back here. And you can see them right in this area back here. I can move back a little bit so you can see. You can see these two here. And then there was a couple others, I think, somewhere in there. You can tell they're that light blue color like that. And if you see them, test them. Now these ones here, if you look, there's 1, 2, 3, 4, 5, 6 of them, 7, 8, 9, 10. These are like a shiny, like duck egg blue, like a real light blue color. They're different. These ones are a little more dull colored, so they're a different resistor type. If you look, they look different. These ones were perfect. They haven't drifted. They're perfect. They don't need they do not need to be replaced. Another thing I want to mention is someone had mentioned that they said that these little plastic caps here, that they were silver mica, and they are actually not silver mica. These are polystyrene capacitors. You can still buy them. They're not as popular as they used to be because they're really delicate. They have very thin leads. They're very not very good with heat. So like if you're soldering these into the board, if you leave the iron on there for too long, you can actually melt these inside and damage them. But the purpose of using these, this is all in that filter stage, you know, for that I showed you in the schematic for the RIAA de-emphasis. And these things are very, very, very high tolerance. They're extremely accurate. They do not drift. They have very low ESR, all that stuff. They're very suitable for that type of an application, and they work. They hold their capacitance even at very high frequencies. So these are perfect for this application. You wouldn't use them in this type of an area where they're used as filter caps, for power filtering and stuff. But to use them in either RF circuits or audio filter circuits like this, like for an RIA, where the capacitance has to be very, very accurate and stay, not have any drift with temperature or anything, these are great. They're called polystyrene. You can look them up. They're a type of film capacitor, by the way, but they're just a special kind. They're different than the polypropylene, polyethylene, the paper foil, so forth. So I just wanted to mention that. Okay, so I'm going to put this up one more time on the screen if you want to do a screen capture to print it up, or whatever. And, it has the little notes and the circles on it and stuff. And then what I'm going to do is I shot a couple of clips of me working on this receiver down here. So, and I did go through the troubleshooting process where I found those bad resistors and things. I'm going to append those clips to the end of this video, and if you are interested in that, you can watch the rest of it. Other than that, I'm going to call it quits for this video, and the next time you see this, it'll be all put together. I'm going to make sure it all works, and then what we're going to do is the next video after this is going to be, this is it for the CA-2000. I'm going to do a test equipment video where we're going to build a novel piece of test equipment, and we're going to use it to compare the performance of this CA-2000 to the other one, which is over here. You can see, if I can move my camera, you can see it's right there. We're just going to compare the two and see how they work. And part of it is to compare, by changing the caps and the resistors, if this thing will perform better, that we can measure it. And it'll also kind of be a test of this test device I want to build and play with. Might be a total flop, or it might be something really cool that maybe some of you will want to copy, but we'll see. So I'm going to leave it at that. Again, enjoy the clips at the end of the video if you want to watch them. If not, this is it. And I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye. Hi, everybody. Welcome back. Well, this video already started out differently than I planned. I was just going to finish up, doing all of the recapping of the couple of boards that were in here, because it's a pretty easy job. Everything's real accessible. It's very easy to work on, and I thought, what the heck? I don't even have to film anything. And I got to this headphone amplifier board. And if you recall, in the part 1 of this series, 2 of the resistors on the power supply were open, just totally open. And they were those funny looking kind of teal blue colored resistors. They were like 10 ohms or 100 ohms at 1 watt or something like that. And I thought it was kind of strange because there really was no reason for the resistors to open, and lo and behold, they were. Well, I get to this headphone amp board, and I noticed 4 more of those funny looking blue resistors, and they're kind of discolored also. If you look at this one, it's just a little bit discolored when compared to this one. And I thought, well, I don't think there's anything wrong, but I better grab the meter and check it. So here's the first one. Remember, these are 33 ohms. See, orange, orange, and then there's a black stripe at the end. There's 33 ohm resistors. That one's high. It's 47 ohms. This one's high. It's 47.6 ohms. This one's horrible. It's 116 ohms. And this one is 66.66 ohms. So what the heck's going on? Now every other resistor that's not those funny looking ones, they're perfect. Like here's a 10 ohm. It's good. 10 ohm. Good. And I can go down the line and they're all good. It's just these kind of teal colored, greenish blue colored ones. So obviously I'm going to have to replace these, but I just thought that was really strange. And if we go to the schematic, and I have my camera on manual focus, I hope it's still focused here. Let's go to autofocus for a second. There we go, let it do its thing. So those resistors are down in here. I didn't even look yet, but what are these? 33 ohms. They're actually the emitter resistors for the amplifier outputs. So those are the emitter resistors for these transistors here, these power transistors. This has a pretty substantial headphone amp. I'm really excited to go over the schematic with all of you because there's some design features in this preamp that you'll understand why this preamp, as simple as it looks, is so highly regarded. I don't know who the engineers were who designed this particular preamp, but when you look at the quality of the circuit design itself, you look at how innovative they were with choosing components that are both affordable but yet absolutely high performance. I'm really, really impressed with this preamp. There are preamps that probably cost 2, 3, 4 times what this thing does, and I doubt that they'll outperform the way this thing is going to work. But anyhow, let me replace these resistors. Again, you know, this is worth seeing because any of you who are going to restore these, you may want to take note that anytime you see these funny looking, these are probably metal film resistors, and they're probably fusible resistors. They're designed to protect the outputs. So obviously they drift, which is something you really don't often see with these metal film resistors, but these ones, there you go. So let me get them replaced. Okay, I'm not crazy. Took them out of circuit and yep, 116 ohms, there it is. And this is what they should be. These are brand new 33 ohm 1 watt resistors. They're all right in there where they need to be. They all match. Perfect. All right, let's get those in there. So anyway, I pulled the transistors just so you know, for your for your own information. A 2SC 1124, those are kind of notorious for gain fade. What will happen is as they age, the gain will start to drop on them. As the gain drops, it'll cause it to draw more current, and you know, you have weird problems. When I saw these resistors bad, you know, being bad, that's the first thing I tested. But luckily, the gain on all 5 of these transistors is good. And yes, even this weird little one here, this little 2SD356, has a center pin that is not the collector. I don't get it. Anyway, now off to this one. These resistors here, these blue ones, they are a different type of different type of resistor. But these 4 here are that type, and these are 5% tolerance, and they are right now, all 4 of them are about 4 to 4.5% out of tolerance right now. So yes, they're technically in tolerance, but they're probably going to drift. So what I'm going to do is I'm going to replace these as well. And I think that's going to get most of these blue resistors out of here. And I have, again, these are metal oxide. Same thing as this board I replaced with metal oxide. So that should make this a lot more reliable. All these other transistors so far seem to be okay. I don't think I need to replace them. And so we'll just replace these and we should be good to go. Okay, we're onto the power supply board now, and it's a little difficult to see, but if you look at this resistor, these are those two 120 ohm resistors that were bad in the other CA-2000. This one is discolored. It's kind of a little bit funky coloring. And although it is good, it's in tolerance, it's reading 125 ohms. This one is reading 120 on the money. It's dead on. This discolored one is 125. It's drifted up a little bit. Again, I don't know if that's a problem or not. I mean, it's really hard to see in this lighting, but I'm going to replace these because it just seems like all of these resistors, these blue ones, are problematic. So they're going to get replaced with the same ones that I put in the other CA-2000 just for good measure. Other than that, a lot of this looks good. These transistors, I may replace them as well, as long as they're not those stupid ones with the backwards pins that don't have the collector in the middle. I have to look it up. Because if the gain starts to fade on these and go down, they'll start to run a lot hotter, you know, and I've read a few comments out there in forums that these are notorious for getting hot sometimes. So we may try to preempt that failure from happening as well. So that's what I'm going to do. Let me get some things replaced on here and I'll be back.